There are moments in astronomy when a single image, a single observation, forces scientists to rethink everything they thought they understood about the universe. Some discoveries roar into history: explosive events, brilliant supernovae, blazing gamma bursts. But others arrive quietly, a small cluster of pixels, a faint glow hidden inside a spiral arm, a detail so subtle it takes years to interpret. And yet, these quiet discoveries often reshape entire fields. When the Hubble Space Telescope turned its eye toward the Andromeda Galaxy, our massive neighbor, the most distant thing visible to the unaided human eye, astronomers expected detail, beauty, perhaps refinement of existing theories. They were not expecting to rewrite them. But that is exactly what happened, because what Hubble saw inside Andromeda did not simply add to our knowledge. It changed astronomy forever. Beat, the music softens, deepens. Before we begin, take a moment to imagine something nearly impossible to grasp: a galaxy, containing 1 trillion stars and stretching across 220,000 light years, approaching us at over 110 kilometers per second. A galaxy that is not just near, but on a collision course with us. This is Andromeda, M31, a cosmic titan, and Hubble's examination of it revealed structures, patterns, and histories that astrophysicists had never seen with such clarity, and in some cases, never even suspected. This documentary will take you inside that discovery, not through exaggeration, not through myth, but through evidence, through data, through the quiet, astonishing truth of what Hubble uncovered and why it matters for the future of our galaxy and our place in the universe. This is the story of a photograph, a mosaic, a decade-long scientific effort, and the unexpected discoveries that followed. Let us begin. To understand why Hubble looked into Andromeda, first we must understand what Andromeda is, not just to astronomers, but to us. Andromeda is the closest major galaxy to the Milky Way, though close in cosmic terms still means 2.5 per million light-years away. It dominates our cosmic neighborhood. It is larger than the Milky Way, more massive, older in several regions, containing far more globular clusters, stellar populations, and debris streams left behind from ancient galactic collisions. Most importantly, we are not separate from Andromeda's future, we are part of it. In about 4 to 5 billion years, the Milky Way and Andromeda will collide, merging into a single giant elliptical galaxy, Milkdromeda as some astronomers call it, or Milkomeda as others prefer. This future merger isn't speculation. It's orbital mechanics, gravity. Inevitable, so when Hubble was pointed toward Andromeda, astronomers were not merely studying a distant object. They were studying our galaxy's future self. The structure of Andromeda is a preview of what the Milky Way may become, but understanding that structure turned out to be far more complicated and far more astonishing than anyone expected. The Hubble Space Telescope is not new. Launched in 1990, it has observed the universe longer than many astronomers have been alive. But when it comes to galaxies, there are 3 things Hubble does better than almost any instrument ever built: resolution, stability, precision. Andromeda had been photographed before, from space, from Earth, through long exposures, through adaptive optics. But earlier images had a problem: they couldn't resolve individual stars in most parts of the galaxy. Imagine trying to study a forest when every tree is blurred into a single green smear. That was Andromeda, a blur of billions of stars. A glowing mass, but Hubble changed that. With its extraordinary resolution, Hubble could resolve tens of millions of stars, one by one, in just a small portion of Andromeda's disk. Suddenly, astronomers could study age distribution, star formation, history, hidden structures, stellar populations, metallicity gradients, debris of ancient collisions, not in theory. Not in averages, but directly, pixel by pixel, star by star. This ability transformed Andromeda from a distant smear into a detailed cosmic landscape. And what Hubble found in that landscape was unexpected. To explore Andromeda in unprecedented detail, scientists launched an ambitious project, the FAT Survey, the Panchromatic Hubble Andromeda Treasury. This was not a simple observation, it was a monumental undertaking. 7 years of imaging. For 150 individual Hubble orbits, 8 filters across ultraviolet, visible, and near-infrared wavelengths, 1.5 million seconds of exposure time, the largest survey Hubble had ever undertaken of a single galaxy. The goal was straightforward, to map a significant portion of Andromeda's disk with such clarity that astronomers could study individual stars the way they study stars inside our own Milky Way, but the result was anything but straightforward. Because when Hubble began capturing these images, when the finished mosaic was finally assembled, it wasn't just the size of the image that shocked astronomers, it was what the image revealed. A level of substructure, complexity, and hidden stellar populations so intricate that it forced researchers to re-examine the entire life story of galaxies like our own. The discovery was quiet, subtle, but profound. It is here, inside the FAT Survey mosaic, that astronomy changed forever. When the FAT Survey mosaic was first assembled, scientists realized they were looking at something unprecedented. It was the largest image Hubble had ever taken, a mosaic containing 1.5 billion pixels. If printed at full resolution, it would stretch wider than the height of a person. And even then, you would only be seeing a fraction of it. This image didn't just show a galaxy. It revealed 31 million individual stars, each resolved as a separate point of light. Think about that for a moment. 31 million stars, each one a world. Each one possessing its own history, its own age, its own chemical composition, its own story. And this was only a slice of Andromeda. Just a few percent of its entire disk, the scale was overwhelming. It was as if someone had taken the Milky Way, peeled away the dust, and zoomed in billions of kilometers closer, until every star stood on its own. This was not a photograph, it was a revelation. A window into the structure of a galaxy in a way humanity had never seen before. And as astronomers zoomed into this mosaic, something became immediately clear. Andromeda was not the neat, orderly spiral they expected. Something strange, something unexpected was hiding inside. A complexity that would force them to rethink the very way galaxies grow, evolve, and survive. Before the FAT Survey, astronomers thought they understood Andromeda's structure, a clean spiral. To prominent arms, a smooth disk, a large central bulge. But once Hubble resolved millions of its stars individually, the picture changed. Instead of a uniform pattern, Hubble revealed a galaxy carved by ancient violence. Hidden inside the disk were tangled streams of stars. Ripples from past mergers, shell-like structures, overlapping rings, massive star-forming clumps, regions where old and young stars mixed in unexpected ways. These were not surface features. They were deep, structural scars, fossils of galactic collisions. Andromeda, it turned out, had eaten many galaxies before. The spiral that once looked calm and elegant was, in reality, a battlefield, its gravitational past etched into the positions of its stars. One of the most striking discoveries was a huge off-center ring of stars and gas, a feature likely created when Andromeda consumed another galaxy several billion years ago. This ring was not subtle. It reshaped the internal dynamics of Andromeda. It modified the orbits of stars. It altered the distribution of dust and star formation, and yet, from Earth, through even the best telescopes, this ring remained invisible. Only Hubble's star-by-star resolution uncovered it. This ring alone would have been a major discovery, but it was just the beginning, because Hubble also uncovered something that astronomers had not anticipated at all. Something deep inside the galaxy's shining core. Galaxies are like archaeological sites, their stars are the artifacts. By studying the ages and compositions of stars, astronomers can reconstruct the entire life story of a galaxy. So, when Hubble resolved millions of individual stars in Andromeda, scientists could do something they had never been able to do before: map stellar ages across an entire giant galaxy. The results were startling. Instead of a smooth distribution, older stars in the center, younger stars in the outer disk, Andromeda showed complex age layering, unlike any galaxy previously mapped in this way. Hubble revealed regions of very young stars far closer to the core than expected. Pockets of extremely old stars scattered through the outer disk, multiple overlapping generations of stars forming in the same region, age gradients sharply broken by past mergers, evidence that Andromeda stole stars from galaxies it consumed. This was not a clean spiral. It was a living, shifting, chaotic system. Some astronomers described it as a galaxy with a double life. A system shaped by both ordered rotation and violent cannibalism. But the biggest surprise, the most important discovery, the one that truly changed astronomy, was still ahead. It was hidden closer to the galactic center, a place where astronomers expected uniformity, age, and stability. Instead, Hubble found something very different, and that finding would rewrite the story of how galaxies, including the Milky Way, are built. Every galaxy has a story, and if you want to understand that story, if you want to know what formed it, shaped it, tore it apart, and rebuilt it, you look at the core. A galaxy's center is its archive, a library of ancient stars, a gravitational well, a quiet witness to billions of years of cosmic history. Astronomers believed they knew what Andromeda's core contained: a dense central bulge, a bright nuclear cluster, a supermassive black hole, and a smooth, symmetrical population of old stars. But then Hubble looked closer and closer, until the core of Andromeda, once blurred beyond recognition, became sharp enough to reveal details no one had ever seen before. What Hubble saw there did not match any existing model of a spiral galaxy, because Andromeda's center had two distinct nuclei, two bright, gravitationally bound star clusters, locked together in an elegant but unsettling dance, rotating around a central point that was not either of them. This was not normal, not expected, not predicted. It was a discovery that shocked astronomers around the world. Hubble's discovery of a double nucleus inside Andromeda seemed, at first, to defy logic. Why would a spiral galaxy, a galaxy expected to have a single, smooth central concentration of stars, contain two? The two nuclei were labeled P1, the brighter cluster; P2, the slightly dimmer cluster but containing the central black hole. They were separated by a mere 5 light-years, an incredibly small distance on galactic scales. Before Hubble, these two clusters appeared blended together. No telescope on Earth could separate them, but Hubble resolved them clearly. To glowing knots of starlight, to dense populations. Two centers where there should only be one. What did this mean? Immediately, theories began to form. Perhaps the double nucleus was the leftover core of a galaxy Andromeda had swallowed. Perhaps the clusters were being stretched by the tidal forces of the central black hole. Perhaps the stars formed inside a rotating disk, split by gravitational instabilities. But as the FAT survey continued, a more profound explanation emerged. An explanation that would permanently alter how astronomers interpret galactic mergers. The double nucleus was not an anomaly, it was evidence. Evidence of a violent event in Andromeda's past, one that shaped its structure and determined its future. The best explanation for Andromeda's double nucleus is also the most dramatic. These two clusters are the remnants of a galaxy Andromeda devoured. Long ago, perhaps billions of years in the past, a smaller galaxy spiraled inward, drawn by Andromeda's immense gravitational pull, until it collapsed into the central region. Its core survived the fall. Its stars became trapped, warmer, more chaotic, distorted by the supermassive black hole, but still recognizable as a distinct structure. The galaxy didn't vanish, it was absorbed. Its nucleus became part of Andromeda's own. Hubble didn't just photograph a galaxy, it photographed a cosmic crime scene. A fossil of galactic cannibalism, a silent record of destruction. Proof that Andromeda grew not through calm evolution but through violence. This discovery reshaped astronomy because it revealed something fundamental. Galaxies are not peaceful systems, they are predators. They swallow their neighbors, they steal stars. They merge, tear, and absorb. They grow through collision. Andromeda's double nucleus became the clearest evidence yet that spiral galaxies, including our own, may have undergone similar events. This changed the way astronomers describe the history of the Milky Way. It changed how scientists model galaxy evolution. It changed how we understand star distribution, orbital dynamics, and the fate of stellar streams. In a single discovery, a pair of bright clusters a few light years apart, astronomers were forced to rewrite chapters of cosmic history. But Hubble wasn't finished yet because deeper inside the fat data, beneath the stellar maps, beyond the nuclear core, another revelation was waiting, one that would reshape our understanding of our own future. When Hubble mapped millions of stars inside Andromeda, it didn't just capture their brightness. It captured their positions, their ages, and, indirectly, their motion. By comparing star clusters, populations, and their distributions, scientists could reconstruct how Andromeda's stars move, how they rotate, and how they are influenced by past collisions. This was not simply a snapshot of a galaxy. It was a story in motion, and in that motion was a revelation. Astronomers discovered that much of Andromeda's disk was not rotating in a perfectly smooth spiral as earlier models predicted. Instead, the motions showed warps, oscillations, twists in the galactic plane regions where stars orbit at unexpected angles. Evidence of gravitational disturbance deep inside the disk, these features did not match what a calm, isolated galaxy should look like. But they did match something else, a galaxy still settling from a major collision. This realization reshaped everything, not only Andromeda's past, but its future and ours. Because if Andromeda had experienced a violent merger in the past, it offered clues about what would eventually happen when it collides with the Milky Way. Before Hubble's FAT survey, astronomers predicted the Milky Way-Andromeda collision would be relatively symmetrical, to spiral galaxies approaching each other, merging into a single, smooth, elliptical galaxy. But Hubble's deeper look into Andromeda's internal motions revealed a far more complex reality. The twisting orbits, the displaced populations, the leftover debris from ancient mergers, all of it showed that Andromeda is still recovering from a violent event. Which means the Milky Way will not be colliding with a stable, evenly rotating spiral galaxy. It will be colliding with a galaxy that is still dynamically disturbed, still unbalanced, still structurally uneven from the scars of its past. This dramatically changes predictions of the shape of the final merged galaxy, the direction of tidal tails, how star clusters will be thrown across intergalactic space, the future orbits of both galaxies, black holes, the fate of our own solar system. Hubble's data forced astronomers to build new models for the future merger. The results were shocking. The collision may be more chaotic, more asymmetric, and far more dramatic than earlier simulations suggested. But that wasn't the most important discovery. The most important finding was something far more subtle, something hidden in the ages of Andromeda's stars. A clue that told astronomers when Andromeda was last disturbed, and how close it came to becoming something entirely different. As the FAT data revealed the ages of millions of stars, scientists discovered a profound pattern. A huge fraction of Andromeda's stars were formed in a single, massive burst. Not spread among billions of years, not scattered randomly across the disk, but concentrated in a relatively narrow band of time, a burst so large, so intense that it reshaped the entire galaxy. This starburst occurred roughly 2.24 billion years ago, the same period when astronomers believe a smaller galaxy crashed into Andromeda and was absorbed. Hubble didn't just show the scars of a collision. It revealed its impact, a galaxy-sized shockwave, triggering the formation of tens of millions of new stars, lighting up the disk, transforming the structure of Andromeda. This discovery changed astronomy for one reason: it suggested that galactic mergers drive star formation on enormous scales, not as rare events but as fundamental processes in shaping galaxies across the universe. And if Andromeda's starburst was triggered by a merger, what does that mean for our own galaxy's future collision? It means the Milky Way itself may experience a similar surge, a rebirth of starlight triggered by gravitational chaos. A future written in the quiet clues Hubble uncovered inside the heart of Andromeda, but deeper inside the fat data. Beyond the starburst, beyond the structural scars, lay a discovery even more profound, a discovery about dark matter itself. Every galaxy is built upon a foundation we cannot see. A structure without light, a mass without color, a gravitational presence that shapes everything, while remaining utterly invisible: dark matter. For decades, astronomers have known that galaxies must contain far more mass than their stars, gas, and dust account for. Without this unseen mass, galaxies would simply fly apart. Their stars would spin off into intergalactic space. Dark matter is the glue that holds them together, but dark matter is not evenly distributed. It forms halos, clumps, substructures, vast, intricate patterns we still barely understand. When Hubble mapped millions of stars inside Andromeda, it didn't just reveal the galaxy's visible structure. It revealed how its invisible framework must be arranged. For the first time, astronomers could see how star populations were shaped by forces they could not directly observe. The result was astonishing. The patterns in Andromeda's stars aligned perfectly with the predictions of cold dark matter theory. But with new twists, new complexities, new evidence that dark matter may form substructures far finer than expected. Hubble had traced the fingerprints of the invisible, and those fingerprints told a story. Hubble's data revealed that Andromeda's disk is not sitting inside a smooth halo of dark matter. Instead, it moves through a halo full of streams, filaments, and clumps, leftovers from smaller galaxies Andromeda consumed. These dark matter substructures act like gravitational currents. They pull on stars, they bend orbits, they create ripples inside the stellar disk. They influence where new stars form and where they do not. Before Hubble, astronomers suspected these substructures existed, but the FAT survey gave them observable consequences. Ripples in stellar ages, warped orbital paths, sharp transitions between star populations, oddly shaped star-forming regions, asymmetries in the disk rotation. These were not random features. They were signatures of dark matter shaping a galaxy from the inside out. Hubble did not detect dark matter directly, nothing can, but it revealed the architecture dark matter leaves behind. A silent skeleton carved across thousands of light years. Hidden within Andromeda's stellar streams, long, faint rivers of stars stretched across tens of thousands of light years. Hubble identified something remarkable. They were rotating differently from the stars around them, as if they belonged to another system altogether. These streams did not match Andromeda's spin. They cut across the disk at strange angles. Their stars were older or younger or chemically distinct from the surrounding populations. The only explanation was clear. These stars came from galaxies that no longer exist. Galaxies that Andromeda swallowed centuries, millennia, even billions of years ago. Each destroyed galaxy left behind not only a trail of stars, but a trail of dark matter, still orbiting inside Andromeda, still distorting the gravitational field. Hubble's observations confirmed that Andromeda's halo is littered with these cannibalized remnants, a chaotic, layered history of destruction. This was transformative. For the first time, astronomers could see the interaction between visible matter and the dark matter halos of the galaxies Andromeda devoured. This data changed our models of galaxy growth. It reshaped predictions of how dark matter behaves. It confirmed that galaxy evolution is not gentle but violent, and that dark matter is the battlefield where those wars are fought. But as dramatic as these revelations were, one mystery remained. A mystery deep within Andromeda's star-forming regions, a discovery that asks a question astronomers still cannot answer. Why does Andromeda form stars differently than the Milky Way? The next chapter reveals why this may be the most important question of all. When astronomers examined Hubble's FAT data, they expected to find the usual structures of a spiral galaxy, young stars along the arms, old stars in the inner bulge, a smooth gradient from hot blue populations to old red ones. But deep inside the mosaic, Hubble revealed something that did not match any familiar pattern. There were stars, bright, hot, very young stars, in regions where conditions should have been too hostile for them to exist. These stars appeared inside the gaps between spiral arms, inside regions with almost no gas left, scattered through the thick disk, and, most strangely, in the inner halo, far above the main disk. This was not normal. This was not expected. This was not predicted by any model of star formation. It was as if the galaxy had pockets of unexpected youth, bright signatures of recent birth in places long thought sterile. To understand this mystery, astronomers had to rule out the obvious explanations. These were not misidentified objects, not foreground stars, not background galaxies, not computational artifacts. They were real. But how could stars be forming in regions without enough cold gas? Hubble had found the first clues. To understand why these stars existed, scientists turned again to Andromeda's violent past. When smaller galaxies collide with a larger one, they leave behind more than tidal streams and dark matter remnants. They leave behind compressed gas, pushed and shocked by gravitational forces. Gas that can fragment, collapse, ignite, but over billions of years, those gas clouds drift. They are smeared across the galaxy like paint dragged by an invisible brush. Some are stretched into filaments, others are thrown far above the galactic plane. This leftover gas, cold, thin, and isolated, can sometimes form stars, not efficiently, not predictably, but enough to create small islands of newborn starlight. Hubble's discovery of young stars in impossible places suggested that Andromeda's last major merger was not a single catastrophic event, but a prolonged, multi-stage interaction, scattering gas across the galaxy in complex patterns. This explains some of the strange populations, but not all, because even with this model, some stars still defied explanation. They appeared in regions where no gas, not even trace amounts, had been detected. These stars required a different answer, an answer hidden deep in Andromeda's internal structure, and visible only when Hubble's data was compared to simulations of galactic evolution. In the aftermath of a galactic collision, something remarkable can occur. Massive gravitational waves ripple through the galaxy, not waves of water or sound, but waves of compressed space, stretching and squeezing the distribution of matter. When these waves pass through regions of thin gas, they can briefly raise the density above the threshold needed to ignite star formation, even if the gas is sparse, even if the region is calm. Even if no star should logically form there, this phenomenon, once theoretical, gained powerful observational support from Hubble's PHAT survey. The impossible stars inside Andromeda were signatures of gravitationally induced star formation, a rare process triggered by the echoes of ancient collisions. It meant that Andromeda's structure still carried the shockwaves of its past, and that these shockwaves were still shaping the galaxy millions, even billions of years later. This was a profound discovery. It changed how astronomers understand where stars can form, how long merger effects last, how galaxies recover from violent events, how star formation can be revived in near-empty regions, the long-term memory of a galaxy. What Hubble found inside Andromeda was not just star-forming regions, but the fingerprints of a galaxy haunted by its history. And yet, there was still more to uncover. because Hubble also revealed something unexpected about the very oldest populations inside Andromeda, stars that predate even the Milky Way's oldest clusters. Their story would reshape our understanding of the early universe. As Hubble scanned deeper into Andromeda's structure, it uncovered something far older than the galaxy's spiral arms. Older than its star-forming regions, older even than many of the Milky Way's own ancient clusters. It found stars whose ages pushed the limits of cosmic history. Some were more than 12 billion years old, nearly as old as the universe itself. These stars were relics from an era when galaxies were only beginning to take shape, when the universe was still dense with hydrogen and helium, and when the first heavy elements had barely begun to form. To astronomers, these ancient stars are time capsules. They preserve the elemental fingerprint of the early universe, the record of Andromeda's primordial formation, the memory of the galaxies it consumed, and the earliest phases of cosmic structure. Hubble's precision allowed scientists to measure the chemical makeup of these stars, and what they found raised new questions. Many of the stars inside Andromeda's halo carried chemical signatures unlike those in the Milky Way, suggesting they were born in small, early galaxies that Andromeda cannibalized billions of years ago. This discovery changed how astronomers think about large galaxies. It suggested that galaxies like Andromeda are not formed in one smooth process, but through a long history of consumption, assimilation, and ancient mergers. Andromeda is not just a galaxy. It is a graveyard of galaxies older than itself. Hubble had uncovered the evidence. Among Andromeda's oldest structures, Hubble detected vast, faint streams of stars, some thousands of light-years long, spanning across the galaxy like pale scars. These streams were remnants of ancient galaxies consumed long before the Milky Way existed in its modern form. Some streams contained stars older than the Milky Way's own halo. Others showed chemical patterns found nowhere else. They were the fossil remains of cosmic building blocks, the fragments of the first generation of galaxies. The existence of these streams revealed something astonishing. Andromeda grew far more violently, far more rapidly, and far more aggressively than astronomers once believed. Instead of forming slowly and peacefully, Andromeda assembled itself through repeated, catastrophic mergers. These collisions tore apart incoming galaxies, dispersed their stars into long tidal arcs. Compressed interstellar gas triggered new waves of star formation, enriched the galaxy with heavy elements, shaped the spiral structure we see today. Every stream is the ghost of an ancient galaxy. Every cluster is a signature of a long-forgotten collision. Hubble's images turned Andromeda from a simple spiral into a cosmic archaeological site, a place where star populations tell the story of a universe still young and chaotic. As astronomers analyzed Andromeda's oldest stars and the tidal streams surrounding them, they realized something profound. These structures preserved the record of a major cosmic event, an event that took place in the first billion years after the Big Bang, a time for which only limited observational evidence existed. The chemical signatures of these ancient stars showed extremely low metallicity, minimal heavy elements, a composition nearly identical to primordial gas. They were survivors of the post-cosmic dawn era, descendants of the earliest star-forming regions, older than many known globular clusters. For the first time, Hubble provided direct observational access to a chapter of cosmic history previously hidden from view. This changed astronomy because it allowed scientists to refine models of galaxy formation, test theories about the early universe, understand how the first structures assembled, trace the branching lineage of ancient galaxies, connect present-day galactic structures to primordial origins. What Hubble revealed inside Andromeda was not just an array of stars, but a record of the early universe imprinted across an entire galaxy. The discovery was so important that astronomers described Andromeda as a living fossil, a Rosetta Stone for understanding how galaxies are built. And yet, there was one more revelation, a discovery that reshaped predictions about our own future. because Hubble also found evidence that Andromeda's past may foreshadow the Milky Way's fate. As Hubble's deep survey of Andromeda came to a close, astronomers realized that the images didn't just reveal Andromeda's past. They revealed our future because Andromeda is moving toward us. Every second, the distance between our two galaxies shrinks by more than 100 kilometers, quietly, silently, inevitably. For decades, astronomers debated what would actually happen when Andromeda and the Milky Way finally met. Would the galaxies smash together violently? Would stars collide? Would our solar system be torn apart? But Hubble's discoveries inside Andromeda, its structure, its motion, its mass, its dark matter halo, changed everything. It gave astronomers the most accurate prediction we have ever had of the fate of our entire galaxy. A prediction built from real data, a prediction shaped by truth. The first stage begins in about 4 billion years. In the night sky, Andromeda will no longer be a faint smudge. It will stretch across the heavens, larger than the full moon, brighter than any nebula we have ever seen. Hubble's measurements of Andromeda's stars revealed its precise sideways motion, the key to knowing how the two galaxies will meet. Instead of a glancing pass, we are heading toward a direct collision. Not violent in the way we imagine, galaxies are mostly empty space. Stars will slip past each other like ghosts. But the gravity between the two giants will tear their shapes apart. The spiral arms will twist, tidal tails will bloom like cosmic wings. Entire star clusters will be flung into intergalactic space. And the sky above Earth, or whatever world our descendants call home, will be transformed forever. Roughly 2 to 3 billion years after the first encounter, the galaxies will swing past each other and loop back again. Hubble's observations of Andromeda's mass distribution showed that the dark matter halos of both galaxies will interact long before the stars themselves do. Like two invisible oceans colliding, the gravitational distortion will stretch both galaxies, warping them into tidal arcs and streams. For any civilization alive at that time, the night sky will look like a living painting, a river of stars flowing from horizon to horizon. A reminder that galaxies are not eternal structures but chapters in an ever-changing story. Eventually, the two galaxies will lose too much energy to escape each other. They will spiral inward, collide, and merge. Not into a spiral galaxy, not into a barred galaxy, but into something new. A massive elliptical galaxy, astronomers call it. Andromeda, Hubble's study of stellar populations inside Andromeda showed something extraordinary. The galaxy already contains the evidence of past collisions. This means the Milky Way isn't merging with a pristine galaxy, but with one shaped by ancient interactions. The result will be enormous, bright, dense, filled with billions of new stars formed during the merger. A galaxy unlike anything humans have ever seen. For decades, scientists feared our sun might be thrown out into intergalactic space. But Hubble's refined measurements changed that prediction. The simulations now suggest we survive, but we move, and our position in the galaxy changes dramatically. Our solar system will likely drift to a new orbit, far from the elegant spiral structure we once called home. Earth's night sky will glow with newborn star clusters, bright enough to cast shadows. A cosmic dawn billions of years after humanity's first breath.